Hi everyone. Let's maybe let the last people to get in. Worries. So we've talked on Monday for the last time, and so you know that the lecture is going to be in blocks, and this is block number 1. I thought it would be a good idea to start right from the main point and get it done with it. So large language models, and what a time to talk about large language models. The lecture today will be fairly high level, just because of course there's no time to go into the details of each single one of them. But if you understand what connects them, you also will see that there's no point in going into the details, because they all rely on the same old idea since at least 3 years. All right, regarding questions, feel free to interrupt me and ask whatever you want, of course, content related. If a question is a bit maybe too long to answer, or perhaps I actually need to think about it, so I can't answer right away, maybe we could take it at the end or even offline. All right, so let's start. So as I said, large language models. And let's start briefly with what even a language model is. So as you know, it's just a model that based on words that previously appeared, predicts the next word. And although this seems a fairly simple task, usually large language models are the best indicator of what the state of the art in NLP is. And I know it's not hard to convince you of that now, but maybe before ChatGPT you would say, why do we care about large language modeling so much? But if you look at the progress in NLP, things really changed when we went from LSTM to BERT, and then from BERT to GPT-3. Because every model that you have for almost any task usually has a language model at its core, and then tries to do something on top of that. And from that, the rule that if you're able to improve there, you're going to see improvements almost on anything else. So what's roughly the timeline? I'm afraid you see the thing in the corner. I'll try to move it a bit more. So if we look back, what we had at the very beginning, probably what you saw in natural language processing, we had bag of words where we put, words that appear in a certain text with no order. Then there was like TF-IDF, at least to identify the important words in a specific document based on the rest of the corpus that you have. Then we slowly moved. We had RNNs, most famous. We had GRUs, we had LSTMs, which were able to have a hidden encoding based on words that would come in sequentially. And especially after LSTM, we had the bidirectional version, which was the bi-LSTM that would look at embeddings coming from both ways. Then we had probably one of the biggest breakthroughs, that was word-to-vec, which was the first dense embedding method, meaning that for once we didn't have to rely on bag of words, which if you know if you just multiply, if you do the dot product between two bag of words, you always get 0 if they contain different words because they're orthogonal. And with word-to-vec, it's the first time that we can embed densely words, sentences, or any token in a space, which means that now we can treat sentences like numbers. And this changes the whole thing in NLP. It's completely context-free. With context-free, I don't mean that the embedding itself doesn't depend on the context, because we have this context that goes throughout the text, and based on that you decide what the best embedding is. What I mean is that the context will be always the same, because you always use the pre-trained embedding, whereas for instance in BERT, every time the context will be different, and this will impact the vector that you will use for that specific iteration. Transformers, it's the first architecture that uses this encoder-decoder. We'll see a bit more about that in a bit. They have self-attention and solves the information bottleneck. And does anyone know what I mean with information bottleneck? Yes, please? Yeah, so you look just at the last states. That's correct. Plus, you can only feed, so this is more an information, like you cannot look at the information that it's too far away in the past. Plus, training is incredibly slow because no matter how many GPUs I have, I need to pass one word at a time. Transformers solve that by saying we can pass everything at once, and I'm going to give it positional encodings. And that's a big step because without that step, we wouldn't be able to have models that have 170 billion parameters now. And then one of the most famous transformers was BERT, which has been there for a long time, has this bidirectional element to it. We'll talk more about it soon. And then, well, GPT-3, which doesn't really have newer ideas compared to the previous ones, is just a lot larger. But the fact that it is larger takes a lot of new things to the space, because suddenly we see that a lot of things that we thought were not possible, they're just possible by having a larger model, even if it doesn't have a much better technology. So this is pretty much what happened until 2020. And, well, the number of transformers kept evolving. And this graphic is not even up to date, meaning up to date 1 week ago, is up to date 3 months ago. So there are at least 30, 40 that are missing. And you can see the number of parameters keeps scaling up. A lot of models share, usually they're part of the same family. What, at least in research, we say, okay, that's part of the GPT family, meaning autoregressive, just leveraging a lot of data, or the bidirectionality, the BERT family, and then there's BART and many others. So they have drastically grown in size, and they belong to certain like branch of thoughts. And that's what I want to talk today, those branch of thoughts. What justifies starting a new one? I guess I don't need to go too much over attention. Just remember that you have this triplet of queries, keys, and values. And based on a certain token, you can look maybe in the decoder, you can look at what are the tokens at the encoder that match in meaning, or whatever your task is, what you're currently looking at. And you have your attention scores, and the attention scores measures, well, how much you should consider that to influence then your output. And the attention is what basically allows you to solve at least the information bottleneck, not the training bottleneck, though, if you apply just to LSTM. Plus, from the NLP 1, you have seen that if you look at the alignment, meaning, okay, which words in the output attend to which words in the input, you also get some sort of interpretability. And you also can apply multiple levels of attention, which is what we now call multi-head attentions, which is what is heavily leveraged in transformers. And especially self-attention, which is found in the encoder part. Okay, so still in the recap, transformer. So as we said, we have this encoder-decoder structure. The encoder and the decoder, they vary for the way the attention works. So as we know, the inputs are passed into the encoder, and there is a positional encoding that basically assigns, with those like sine and cosine function, additional values depending on where that word is positioned. And these adds what we call positional context. We still feed the entire sentence all at once, because now we can encode the position this way. And then we have a multi-head attention for intra-input relationship, meaning that we already calculate how every word in the input attends to every other word in the input to basically get inherently the structure of the input. Then the decoder is the same as the encoder, but while in the encoder every word was able to see every other word in the input, in the decoder that's not the case. So we mask future words from what the current word can actually see. So for instance, if I'm the word in position number 5, in the encoder I'll be able to attend to every other word, whereas in the decoder, since I'm trying to generate the next word, because I'm doing language modeling, I will only be able to see what's, well, the previous words. You also have encoder-decoder attention, which is, as in the case of a classic attention, is what can give you alignment, and also what learns it. And finally, after all these blocks, which have other linearities and normalization steps just to facilitate training, we have the last linear layer, which is what matches the hidden distribution to the vocabulary size. So we have a score for each word in the vocabulary. Softmax, we go to probabilities, hence That's how we do language modeling. Transformers have had a very, very strong performance compared to methods that we have seen before, particularly because we could train in parallel, and therefore now we could really use a lot of data. The most famous, probably, you've definitely done this in NLP 1, BERT, which is nothing else than a transformer encoder, meaning that all words are able to attend to every other word in the input sentence. And then you might ask, okay, but how do we even train it if we try to generate the next word, but we actually know it? And the trick that they use is that BERT is a masked language model, meaning that we insert masks at several points, and then we try to predict what token would be there. And we can do this bidirectionally. That is the first thing. And the second thing is the next sentence prediction. So intra-sentence, we try to predict the missing word. And for next sentence prediction, we're given a few options of what could be the possible next sentence, one of which is the actual next sentence. And we try to predict whether, oh, it's this one or it's not this one. There are two BERT versions. What we back then thought the large one, 340 millions, and the smaller one, 110 millions. These are, by today's standard, fairly small models. And so, in a nutshell, BERT is a lot of data that we can now finally leverage. Masked language model, so I can use bidirectionality. And next sentence prediction, so I can use context beyond the sentence that I'm currently looking at. And of course, it's a transformer. The logic beyond BERT was, I want to pre-train something once because I have a huge corpus. This is something that Google could do. We cannot do it with a laptop. And then I'm just going to fine-tune it for the task that I currently want to solve. So pre-train once, fine-tune many times, which is of course a lot faster than full training. And that means I train once for language modeling, which is what you train BERT for. It cannot inherently do anything else. And then I just use it, well, with extra layers on top to do sentiment analysis, hate speech detection, name entity inference, recognition, sorry. And that it works fairly simple. But that still means that for each task that I do, I still need one specific version of the layers that I use on top. Because if I do sentiment analysis, means I need to have those weights that I use on top of BERT. If I do another task, of course, those weights, they don't really hold anymore. I need to use other weights. And this is a problem that GPT wants to solve later on, as we will see. There have been extensions of BERT. First of all, there's Roberta, which it's just a more robust version. Very briefly said, it just uses larger data batches, and also doesn't really use the next sentence prediction, which it seemed like it wasn't really the core of what made BERT so good at language modeling. Then span BERT, which just says we just make masks span across multiple tokens. That way we should be able to learn context better. And finally, what, at least in our group, we've used a lot, Distill BERT. Distill BERT just uses a teacher-student mechanism, meaning we get an input, we ask to BERT what the output would be, and that becomes our label, and then we use that to train. And thanks to that, we can take the knowledge of a much larger model to a simpler one in a process that is called distillation. And we can reduce the size of our model a lot while pretty much keeping almost the same performance. And Distill BERT has been used a lot because you could almost run it on a laptop and it would still get BERT level performance. So at least personally, we've used it in a lot of projects, especially in lab courses and practicum. Yes? That's a good question. So no, so you're talking about the hard label, meaning I have, in this case, language modeling, so I have the next word that I'm trying to predict. We do not take that, but rather we take the soft labels, meaning the distribution across the vocabulary that BERT is predicting. And then by using a loss like the KL loss, we can measure the difference in distribution between what Distill BERT is outputting and what BERT does. And this, of course, allows you to leverage a lot more fine-grained information than just, oh, that's the predicted word. Okay, so coming away from BERT to GPT. The first GPT actually dates back, I think, to 2017, 2018, so it also has its years. It has developed in parallel to BERT, and in this case is a transformer-based decoder. So it's autoregressive, meaning that the attention masks do not see what comes after, but simply back to the definition that we've looked at the beginning of language model. It just looks at the previous words and tries to predict the next one. Nothing more than that. And this idea will actually stick for quite a bit. It requires, of course, a lot of training data because the size here starts to go up. And it's quite suited for text generation. It's more suited in text generation than BERT. Why? Because BERT is very used to learn from the context to fill in words. Whereas GPT is more used to predict the next word. So that naturally applies more to text generation than just filling in the gaps. And then going to GPT-2, there are not big changes except the introduction of meta-learning, which we'll leave there as a term for today. That will be in the next lecture more specifically. And similar architecture, nothing new really brought to the table. However, task descriptions were given together with a sample to see if they could see a generalization in terms of what the model would do. So we don't actually have to train for that task, but maybe if I give in the input what the task is, it should be able to perform it already as a language model. The experiments didn't look too good compared to what other models could do at the same size. But what we've noticed back then is that, well, scaling up in parameters seems promising because this generalization starts to somewhat apply when you have a larger size model. And of course, that was just the idea to do GPT-3. So if you take GPT-2, you make it a lot bigger, you use then a lot more data and computation, that's pretty much what you get. So again, the idea hasn't really changed that much yet. It's still an autoregressive model that tries to predict the next word. Yet if I give it 100 times more parameters, I start to get something that is really good in performance, and it can start to generalize to tasks that it has not seen. And that was exactly the motivation that led researchers to actually develop GPT-3. So the previous state of the art, as I said, even if we take BERT, which was pretty much almost the best you could get at the time, you had to substantially fine-tune for a specific task. And then the weights that you would need to fine-tune, those only work for that task. Or if we look at even smaller versions, Elmo, which uses an LSTM as a language model, and then you had to build something on top of it, even more complex. These required a lot of computational effort to perform those tasks, and you had to do it every single time. Whereas you still need task-specific datasets, and datasets have been the bottleneck of the whole NLP and pretty much any other machine learning field for a long time, especially in supervised learning. And more than anything, when you deal with these task-specific datasets, they have a very narrow distribution in terms of what tokens they contain, meaning that you're not really leveraging the full power of your language model, because your language model has seen a lot more data, but in order to predict what's necessary in your task, there's a lot less data that is needed, plus it gets really specialized for that bit of data, and out-of-domain performance is pretty much random. And the last point is that, well, as humans, we are what we from now will call few-shot learners, meaning we need a few instances of a certain problem to start performing decently on it. And that's not what language model did up to this point. And that's exactly what the title of the paper of GPT-3 is. Language models are few-shot learners, which says that if you scale up the size of your model, then you can pretty much start to perform well on tasks that you have barely seen, meaning you see 2 examples and then you can perform it, or even that you haven't seen at all. And for those of you who are not familiar on how to do this, it's called prompting. And before ChatGPT, that meant a completely different thing, and that will be the core of the next lecture. As I said, architecture and size, there's nothing new in terms of architecture. Autoregressive model trained on language modeling. As you can see, the difference with BERT is that with BERT you have access to all words, whereas with an autoregressive you don't, just to the previous ones. So if you want, GPT-3 is even less sophisticated than BERT. Although it performs better because what's known as GPT-3 is 175 billion large. There are several versions that have been rolled out for mainly research or for who couldn't really afford that computational power. But when we refer to GPT-3, we mean the 175 billions, or also known as Da Vinci model. So to do a final recap and comparison of what we have so far, BERT, the size, 340 millions, fairly small by today's standards, and roughly 3 billion tokens for training. GPT-3, almost 1,000 times more parameters and almost more than 100 times more training data. Architecture, BERT, we've seen bidirectional. We use the masked language model technique, and it's made of encoder blocks. So we have access to all words in the input. GPT-3, autoregressive, made of transformers, decoder blocks. The training, as I said, masked language model plus next sentence prediction, although I would really like to point out that the next sentence prediction is not the driver of performance. Whereas GPT-3, simple language modeling. Usage, BERT is still kind of a great contextual encoder, and then you fine-tune extra layers on top of it for the tasks that you need. GPT-3, you use it as it is with prompting. Yes, there is a question there. So simple language modeling, I guess we're clear. You have all the previous words, you just predict the next word. Next sentence prediction, so 2 sentences are actually passed to BERT. The first one, and then you just want to predict if the next one is actually the next sentence. So the second one is a binary task. You can see that way, although the differences are a bit more, because one is a binary task, like yes or no, that is the next sentence. Whereas the other, you actually compute a distribution across the entire vocabulary, because that's what language modeling is ultimate. It never happens that we predict exactly what the next word is, but you get a distribution, and then you have sampling techniques. Yeah, and that's a whole other chapter. You have the concept of temperature. We will not really go into that, but that's the main difference. There were many applications of GPT-3 already when it came out. I don't need to convince you of that right now. Back then, maybe I would have to. The first one was GitHub Copilot, which was pretty much GPT-3 for generating code. And it was the first time that we really saw code generation working very well. AI Dungeon, it was a very fun text-based adventure game creator where you would input a text and it would create pretty much your levels with interaction via text where you need to get through it. And I think there was also a lecture in the NLP 1 about DALL-E 2. That was the big step forward, where you go pretty much we've managed to understand how image and text are sort of correlated in the same space. And therefore from image, from text prompt, we can generate an image. Now there's ChatGPT and all the rest of the famous stuff. Limitations of GPT-3. It's really not good at writing short stuff. Sometimes it's really convenient for it to just keep generating, and once you keep generating, you start repeating at some point, and it ends up saying a lot more than it should, which is also why it also easily hallucinates. Often the hallucination comes from the fact that you always need to predict the next word, which probabilistically looks like a good choice, and therefore at some point you're going to start making things up. And in terms of common sense physics, location, and what happens if I move in a certain room, like that space awareness, GPT-3 also looked pretty bad when tested. Limitations on the general side, you still have the biases, racial, gender, and on the religious side, when you use it. So still problems on that. Size doesn't seem to solve the issue. It's only trained on text, so we have no knowledge groundness, which means that then that's why it also can easily hallucinate. And it seems irrelevant, but it's still a very large model. Like, not many 2 years ago could train a 175 billion model. And lastly, one last question. If it can perform, although on average much better than BERT, are there still some use cases for which BERT is still better? And as I said, definitely not for text generation. But when it comes to classifying a sentence or maybe a specific tokens, it's usually better because it has access to a larger context, meaning also the future context. Whereas in GPT can only rely on what it has seen. So if you have which in context in a specific sentence, you will only be able to classify that sentence correctly if you reach the portion where the context has already switched. And same for filling gaps tasks. That's quite, it's self-explained. Yes, there's a question? No, we're still comparing them in their full sizes. So GPT is a lot larger, but also we're comparing them on different training techniques, because BERT has probably been fine-tuned with some extra layers. GPT-3 hasn't. Exactly, and I mean, this is more a rule of thumbs. Of course, depending on the data set, of course, if I give you 3 data points, GPT will be a lot better. If I give you a lot more data points in a specific data sets, probably fine-tuning the old way with BERT was going to work better. But these are just rule of thumbs. Like, in general, BERT is still useful for those cases, but on average, GPT-3 is a much better language model. Well, bidirectionality in general is the issue of GPT. BERT is just like a very good instance of bidirectional transformer. If there was something else, it would work the same, but there's not really a lot. Okay. So yeah, this was pretty much what maybe you knew already up to 2020. So what comes next? One example, which I've put already in the category of following LLMs, but it's actually not after GPT. This comes slightly before. This was the 2019 Google research paper, I would like to say, called T5, coming from the name. And in that paper, they really explore which combinations actually work best. So they tried bidirectional autoregressive prefix, which, if you don't know what it means, it's just that the first the first part of the sentence is available to all tokens, and after that it behaves autoaggressively. Then they looked at masks, length, mask frequency, training objectives. They tried all of that, and they saw what were the best combinations in terms of language modeling. And then what they also tried, they tried to append a task prefix together with the sample that was provided to the model, which is that was the first time that it was done. Then after GPT-3 became the standard, but they were able for the first time to do multiple tasks with the same language model without retraining on specific data sets. So I think in this case, it was summarization, machine translations, and other ones. Then a model that I actually like a lot, Retro. Retro is able to bring down the dimension of GPT-3 by simply accessing training data at inference time. Let's go a bit more in detail there. So if I take a large language model, I give it a prompt, and it's going to solve it. But of course, it's not going to access training data. It's just based on all the weights that it has, meaning that we know that inherently the data is encoded in it through its parameters, but it's not going to explicitly look at the training data once we just use it. And the idea behind Retro is, well, if I can explicitly access training data when I need to solve a certain task, maybe I don't need so many parameters. And they were actually right. So the architecture of Retro is very similar to the one of a language model. There's a slight difference in the retro blocks, but the main difference is that the input is also passed to what was called a KNN retriever, which looks at your knowledge bases, which is going to be a lot of documents, and then based on two BERT encoders, will find the most similar content to the sample that you're currently considering, and it will generate a latent vector for that, and that will be used to condition your current inference, which allows you to access that information with a much smaller weight set. So for instance, Retro only had the 4% of GPT-3 parameters, but it still performed on par when the training samples that you had available were of decent quality. And plus, it allows you to distinguish between two things. There's language information, which is what language models are really good at, and then there's factual information, things that are factually true if they're stored and if we believe what's in the data set. But language models have only seen it by iterating over it a lot, but they can't actually retrieve it. Sorry, let's remove this. And Retro, since it explicitly does that, we have actually embeddings for both. So you could, in theory, also look into the different embeddings and look, okay, what have we learned in terms of language and what have we learned in terms of facts? And maybe some of you, like Retro was really useful back then, but there's something really in the last months that came out and is really inspired by this logic. Does any of you have a guess? What, sorry? What? As well, there's one more, even more popular. Yeah, it is. So AutoGPT uses that, but the first step was the ChatGPT plugins, which then AutoGPT uses. So yeah, plugins pretty much follows the same idea. It says, if I give ChatGPT access to data at any time, or even to browse the internet, that doesn't even, like I don't care about storing things long-term. So it's like giving long-term memory to ChatGPT. And potentially you could now bring down the number of weights of ChatGPT. There's just no point in doing it because we have available that computational power. Then something that it's more famous than image domain, and that's how I will briefly explain it, but I think has a lot of potential for the text part as well. Stable diffusion. Briefly switching to computer vision, we have an image, we apply noise to it iteratively until we have lost most of the information, and then we train basically transformers blocks to denoise the image until we have retrieved the original one. And what you can do with models like BERT or CLIP, you can influence that latent embedding to go from text to image. And while stable diffusion is really, really good at creating images, we haven't really seen super strong applications on text yet, but they are coming out. And now you're thinking, why do we care about the image model? We're here to talk about NLP. And the point is, as we see that, as we denoise the image, we're still in a continuous space. We know that NLP, that's not really a possibility. So you have to apply tricks to, discretize your intermediate input. But the reason why I think stable diffusion has really a lot of potential is because we have lost that autoencoder strategy. Autoencoder, as well as it's working, it still relies on predicting the next token. And that is, for factuality, really bad, because I have this much of information and I try to predict the next token. I don't know what's coming next, and probably the next token that I'm generating prevents me from generating something factually true because I don't know what's coming next. It's like when we talk as humans, we know where we want to go, and hopefully our discourse and articulation will bring us there. Autoregressive models can't do that. They hopefully they want to go somewhere, but they can only generate the next word, which probably puts a limitation on what comes after, just for statistical inference. And Stable Diffusion will give you the chance to generate entire sentences at once, because then you're pretty much denoising concepts to entire sentences. And here, of course, what I'm talking about, it's fairly fluffy because we don't have those exact applications yet. But that's where probably the potential of Stable Diffusions relies, not having to predict only the next word, which pretty much eliminates the next bottleneck of all large language models, the fact that you have to predict always the next word. Finally, as many of you know, ChatGPT, I probably do not need to introduce it. It comes from GPT-3, probably actually the 3.5, which is already improved. And it did supervised training on dialogue first, meaning that they had GPT-3 interact with human annotators, and annotators would actually write down the ideal answer in a chat-like format for a specific prompt. And so GPT got first fine-tuned on this type of data. Second, they took a more automatic approach. They said, okay, for each prompt, I'm going to take many possible outputs, and then I'm going to let human annotators label which one is the best. And based on which one is the best, I'm going to train a reinforcement learning policy that pretty much rewards better prompts or better answers. And once I have trained this policy, once I've trained this reward function, I can just use it in a reinforcement learning policy setting. So I can get GPT-3, which has been already tuned more for chat-like application. I let it generate the an answer with the policy. The policy answer is fed to the reward system. The reward system is going to say good if the prompt was probably one of the chosen by the human annotators, and it's going to say not good if it doesn't really fit that criteria. So this reward function tries to mimic what human annotators would say about the utility of a certain sentence. And that's why ChatGPT is a lot better than GPT, because for the first time we have this reinforcement learning loop that tries to really mimic human feedback, which a lot of the times is based on actual utility of what I've asked you, regardless of, oh, this is a very nice and long grammatical sentence, but oh, this actually interacts with me in a very natural way, and it contains the information that I was looking for. Other facts, so these are facts that I've put down in January, but we don't actually know a lot more than this even now. So ChatGPT, I assume it doesn't probably remember previous prompts. They're actually remembered by the application itself. So they're just fed again once you get a new prompt. How they manage to not have a bottleneck, meaning that the longer the conversation gets, ChatGPT doesn't get slower. I am not sure how they manage that. They have acknowledged, however, that it can produce false information or even completely make up facts. And you can still jailbreak it. So it's not really going to give you financial advice, for instance, but if you can tell it, oh, can you please act like, I don't know, who's a famous financial, Donald Trump, and speak in its own way, that will trick ChatGPT of going out of its like breaks and really tell you anything that you want. Then notable mentions. So these are models that I didn't think were worth having their own slides, but I still would like to mention them. First of all, this Palm, which was also pretty large by Google. I don't think there's a lot to say about it, except that it used this graph-based encoded knowledge, also retrievable at inference time, so that the sentences could be a bit more coherent and a bit more fact-based. Then Bloom, which is actually used a lot in research. And first of all, because it was the first large language models to be truly open source. And it was an incredible collaboration of Hugging Face, Big Science, and a lot of entities also at the European level. And it's really good at multilinguality, just because of how well the data set that was used for training was put together. Then Galactica, which is from Meta. And this is just a large language model that was trained specifically to generate text of scientific type. So it's really good at generating scientific papers that pretty much look like a human would write it. And that's also why they had to take down the demo. And finally, OPT, which is from Meta, that didn't really get a lot of attention because Llama came out fairly quickly up. I mean, OPT's been there for a while, but there was a long wait list. I never got access to it, for instance. And then Llama came out and it seemed like a lot better. And they had also quite a bit of a focus on trying to get a smaller carbon footprint, so a model that would actually run a bit more efficiently. And this was the situation in January. But as I said, that's like January, February, that's when I was doing my slides. But then someone said, are we going to talk about? I said no, but I couldn't resist. So I still have put what I think are the 6 biggest pieces of news. I hope I got the best 6, probably not, but still I gave it a try. Llama came out from Meta. So Llama is a competitor to the GPT family as a whole. It's more an instruction following large language model. And they made it free for researchers. As a matter of fact, everyone could use it. And then before we go to Alpaca, there was the BARD, which was the ChatGPT answer from Google. So this is more like a chat-like large language model. Still 137 billion parameters, so fairly large. And then one of my favorite, Alpaca, which I believe really changes the way we see how large language models can be developed. Because what the people actually, I think a few grad students at Stanford did, they took Llama, which is free, and then they say, we can just keep prompting ChatGPT or GPT-3 or 4 or whatever is available through the OpenAI API to get good human labeled data. And as much as we can say, oh, but human labeled data is for sure better than automatically labeled, that's actually not really the case. Human labeled data is not as golden as we would like to think. And so they kept prompting the OpenAI API, and they used that data to fine-tune what then they called the Alpaca model. And Alpaca is 7 billion parameters, so fairly slow. They actually took very small. They took the smallest version of Llama that was available, but it also performs as good as the Llama. And it's also not too far from ChatGPT. But the big revolution here is that Alpaca was trained with roughly $500, $600, which is nothing compared to millions that have been spent on developing the GPT-3 family and Llama as well. Which means that if you're able to leverage the data cleverly and the models that already exist, almost anyone could actually jump into the space and create their own large language model. And that's why Alpaca was really funny to see how just a few grad students from Stanford could pretty much replicate the performance of a company that is now worth billions. There was a question in the back, yeah. Yeah. Yeah, it's the same architecture, same parameters, but then you're prompting, but you're still fine-tuning the parameters with it. Like prompting is a way you can get a loss. Then whether you use it just to doing context learning, all stuff we're going to see in the next lecture, or whether you actually fine-tune the parameters with it, that's a different case, but in this case they were fine-tuned. As far as I understand, yes. So just some fine-tuning, because of course the Llama models are already trained. But yeah. And Alpaca is an instruction following model, meaning it's more like GPT and not ChatGPT. Then the same idea, because Alpaca made their data set that they got out available. Dolly, which came out like a few days ago. And this was one of the open source ChatGPT-like model. I think it was GPT-J. oh yeah, 6 billions. And then they used the alpaca dataset to actually make not something that works like ChatGPT, but still fairly decent for just being at 6 millions, and also considering it took them a few days to create. In the meantime, on the other side of the spectrum, GPT-4 came out, so we don't actually know how big GPT-4 is. But I think also that the level of how much it is better compared to ChatGPT has been downplayed, because of course if you use it through the AI, through the UI, it doesn't seem like that much different, but the factuality of it, at least by personal experience, seemed a lot more on point. I would guess it's bigger just because the UI goes a lot slower, so that would justify why. But yes, that's pretty much everything there is to say about it, because we don't know anything else. And finally, I think it was mentioned also last time, AutoGPT, which is an attempt to get as close as we can right now to what we call AGI. And the idea there is I'm going to take GPT-4, I'm going to give it access to even my file system if I want to, and also the ability to search on the internet. And this does what the GPT UI cannot do, because that's, they stop, I think, September 2021. They cannot retrieve any information after that. But if I give that ability and also the ability to auto prompt, so to prompt itself iteratively as much as I can, it can not only solve one-step tasks, but it can break down a goal into multiple tasks and then figure out how to solve every single step. And yeah, I've just played a bit yesterday evening. I played with it yesterday evening. I'm not sure actually what the potential there is yet. There was a question. That is a good question. I do not know. There's probably a lot of caching that is done, but I definitely don't know the details there. So AutoGPT also is able to save data a lot locally. So I can't really hear well from here, but the fact that you can save data into text files means that you're going to condition later iterations of, well, what you're trying to do, because you can access it locally and you don't need to search on the internet every single time. That speeds the process by a lot. The details, again, I don't really know them that well. Yes, we start to have maybe a bit too many questions. Oh, we still got time. Yes. Probably not. No. So I would shut down the whole AGI, because it depends on the definition that you have of AGI. If someone tells me, oh, AGI means performing like a superhuman, calculators can perform like a superhuman on a specific task. Performing like a superhuman on many tasks. ChatGPT, then it would be already considered AGI. I believe it's beyond that. I don't believe it's necessarily connected with the concept of being sentient. I think the two are still kind of separated. But that depends on your philosophical definition of what AGI is. I don't really think so. I don't see anything that would stop it from doing it. The one from before, it was like, what makes AutoGPT so fast as it performs multi-step tasks? Hmm? What do you mean, why would you? The point is, it's not slower. Hmm? Yeah, but it's not faster. That's not the point. Like the point is when you have so many contexts open, right? Because you have the database, the vector database that you can query. You can access the internet, which is a lot larger than a prompt. So the more information that you can access, you feel like your context window is getting a lot larger. Then intuitively you should be a bit slower, but it isn't. It's actually pretty fast. And the question, I think, why is it not slower? That's how I understood it. And the answer is it's not slower, which I think it's known. I think it's probably very optimized, but I really don't know the reasons behind that. I was trying to add all this information the last days, and funny enough, I was done yesterday around 10 p.m. And as soon as I was done, there's a new model released by Stability AI. I decided to go to bed and call it a day. But yeah. Yes. I'm sorry, I mentioned what again? Yeah. Like, so you're asking me why jailbreaks work? Is that the question? How they're setting it? That would be, I mean, this is OpenAI mostly doing it. I think also BART is quite good at it. I do not know how they set it up. This is probably proprietary knowledge. At least I don't know how they do it. Okay, so we've had an overview of, well, some stuff that has come out. I'll probably wait a bit for another question. So can we look at everything that will happen, at least try to get some trends? Like, okay, what's the overall message here? Well, the first thing is that no matter what models we've looked at, they all, well, with the exception of Stable Diffusion, they all rely on attention quite heavily. So attention, which is the core mechanism of transformers, is still the core mechanism of the latest stuff that we can see in the NLP space. So probably attention's here to stay for a while at least. I haven't really seen anyone trying to go away from it. We've seen different training strategies, different sizes, different data, which is crucial, but the attention mechanism hasn't really been questioned for a bit. The second thing, which I wrote down also like in February, is that large language models will keep scaling in size, and there will be hopefully more open source options. So yes, we've had more open source options, but if I look at that thought now again after what happened, I am not sure that scaling in size will be the most profitable direction for research. Because yes, you have GPT-4 that we assume is larger than its predecessors, but Alpaca and Llama versions that still work very well, they have substantially smaller sizes. They have just seen that they can obtain decent performance by not using human annotated labels, and also training for longer. Then there's also a lot of research that will probably go into training on larger and higher quality data, which I think is the reason behind Alpaca's success, and also why Bloom is so good at multilinguality, because of how much work they've put into that dataset. And then something that is quite speculative, but I do believe that autoregressive is not the way to go. It might be the way to go for a bit, but I don't think it can last much longer, because just predicting the next word doesn't really seem that clever. I mean, it's the best idea we have so far, but it seems like there has to be a better way for factuality, but also for actually timing. Rerunning the entire forward pass every time I need to generate a new word is also quite slow. Then one thing that we obviously see is that architecture details become more and more irrelevant. There was a big gap between GPT and BERT in terms of the strategy that they employed. But since then, you've had slightly different strategies, but it's still this autoregressive idea that keeps to prevail. So it's what seems important are not the details, but rather the broad architecture type. the training objective, the fine-tuning techniques, so how do I use the data that I have available, and probably the most important, data quality and quantity. What we already see, but we're probably going to see it even more, is the modality and linguality. If you can use multiple languages and multiple modes, that is also what a lot of work and also funds are going put into. So we've seen already DALL-E. We've seen, I think, GPT-4 with plugins. You can pass an image as an input and we'll use it for generate text. And I think also the eco-friendliness, or like trying to reduce the amount of energy or the amount of iteration needed to build one of these large language models, will be at the core of a lot of researchers and companies. And probably the biggest change that I have observed since I started my PhD is we do NLP in a completely different way. Back then we would, let's take bidirectional LSTM, BERT, whatever. I'm going to take a data set. I'm going to train it on the data set. I'm going to decide what labels I want to use, what data set I want to use. That's not really something we do anymore. We just take pre-trained models and we find a good way to use them in terms of prompting or few-shot learning to a new task that we're given. And this is something that has drastically changed. It doesn't even matter having GPUs anymore, because no one really does training except a few companies. And of course, even like if we think about training from scratch, we can pretty much forget about it. Like, unless you're one of the big players, you could potentially do it if you really wanted to, but I don't really see the point. And that's how NLP practitioners have changed in the last years. Okay, now let's take a few of the questions. I think there was one there. Mm-hmm. So basically just by using a smaller part of the document that has been embedded, that's how you speed up search. Mm-hmm. Okay. That would make sense, like why they haven't lost any speed in stuff like AutoGPT. How do you define the top? Mm-hmm. I mean, I see an issue with that, but maybe let's take it offline, just because of square complexity still. Yeah, sure. Mm-hmm. Mm-hmm. Well, there's no way to know. I mean, at least for me, it would seem quite practical from their perspective to just reuse what they know so far. Also, they have declared that they have solved issues of the previous version. They've claimed way more that than saying, oh, we have come up with a completely different model. And otherwise, I really don't see anything else that doesn't use attention. Possibly, yeah. Yes, maybe one last question there. The answer is very complex. So how do we compare large language models? It's definitely a topic that we have in the next lecture. So you can compare them across many tasks, and that's one way to do it. So you have this like cross tasks data set. We will go more in detail next time. However, the way the major players have done it is just by putting them, like testing them on the same thing. GPT-4 was compared to GPT-3 on passing the bar exam of lawyers in the United States. That is not a usual benchmark. So that there's not, I mean, there are some benchmarks, but I wouldn't say there's one benchmark that it's always been used and we have a clear standard for it. Which raises also another problem, and is many of the models that we compare often have a different size. They're all in the realm of large language models, but some are 5 billion, some are 200 billions. Is it really fair? From some perspectives, yes. From some perspectives, no. So the answer is way more complicated. Okay, so research directions that have been coming up in the last, well, years. Well, first prompting, which wasn't really a thing a couple of years back. Auto-prompting is now a new thing. And fine-tuning techniques, which is what the next lecture is about. Post-hoc explainability, which means how do I explain the outcome of a model that maybe I don't even have access to. And then we have, well, robustness and adversarial attacks defenses. There's the topic connected to this of jailbreaks and security of these large language models. And then there's model distillation, which maybe now it's a bit under the hood, but if we think about it, Alpaca is a distilled model from, well, the GPT API. And then low resource language tasks, which I think is going to be one of the main topics in the next block. And then augmentation and integration via knowledge bases, because we have all these pipelines to create new large language models, but to ground it actually in facts, we will need data that is retrievable at inference time. That's one of the ways. So definitely knowing how to integrate that via having vector databases or something of that sort, it's still something that probably will be relevant for definitely a few years. And yeah, so in the slides you will find the references, a link to the main papers that we've used. And yeah, these are the study approaches if you want to, well, go through this lecture. And I think that was it for the day. And I will see you next Monday, where we're going to talk about fine-tuning and more in general, fine-tuning techniques and prompting. Thanks.